All right, I'm going to shift gears a little bit here. So I'm going to start off by explaining a little bit about who I am, and then that's going to make a lot of sense about all the crazy things I'm going to say. So my background is actually in philosophy and cognitive neuroscience. That's what my PhD is in. So I moved from the philosophy department to the behavioral neurosciences department to study behavior genetics and primarily behavioral endocrinology, and then moved in my postdoc over to the Department of Industrial Engineering to work on multi-sensor data fusion. So philosophers talk too much and are too opinionated, and engineers show too many slides. Unfortunately, you get the worst of both worlds. So with that, what I'm going to talk about a little bit here is not only some stuff about technology, what we're doing at OSTHUS. I'm going to talk a little about the Allotrope Foundation, which some of you may know about, but I'm also going to talk a little bit about some things having to do with business value and aligning these things across different kinds of corporations. And having worked in areas such as petrochemicals, health insurance, pharma, medical device, national defense, and so on, I see nothing but connections across all of these different verticals. Everyone has the same 10 problems. My job is usually just organizing those in the way to attack them first. So we're going to look at the current laboratory data situation, which I think everyone in this room will kind of agree is a bit of a mess. We're going to look at the growing importance of data as a corporate asset. We're going to look at what semantic technology is and how it can help, because I think there's a lot of confusion. The word ontology already came up. The word philosophy was used in the last talk 2 times. And we're going to talk about moving beyond semantics, because semantics is not the answer. Semantics is a tool. And this is coming from a card-carrying semanticist. I've been working in semantics since the 90s. The reason semantics has not worked up to this point is, frankly, because we couldn't scale. We couldn't scale. We couldn't do anything more than solve toy problems. But now with the dawn of big data, with Hadoop, with cloud computing, with things like this, and the rise of analytics that are coming about, I'm hoping to show you some ways that we can utilize the semantics in a reference data setting to be able to do some really, really interesting things with advanced analytics and move beyond to what I think is going to become the smart labs of the 21st century. So part of this is going to be visionary, part of this is going to be innovative. I'm a part-time professor at NYU. This is what I teach in, is an innovation. With that, let's look at where we are. Many challenges exist today. I mean, we're all familiar with people's desktops that look like this, right? Full of Excel spreadsheets. It's full of personal calculations. People build their own data silos around themselves. And then they're inside of a department, which is perhaps another data silo, which is in some division, which is perhaps another data silo, and so on and so on and so on. So these data silos are actually insular. They're inside of one another. You also wind up with incompatible instruments and incompatible software types. Right? This is what the Pistoia Alliance and the Allotrope Foundation is trying to overcome. Right? Instruments don't talk to one another. The chromatography machine doesn't talk to the weighing device, and so on and so on. Legacy architectures exist. We have to deal with these. You can't throw your old systems out. You can't throw your old data out. But building bridges between them is incredibly hard. Doing point-to-point mapping is not going to work anymore. There's too much data, there's too many systems, and those things are rigid and brittle. When you build them with point-to-point mappings, what happens in a few years? You have to redo it. And every time you have to redo it, the cost goes up, and so does the complexity, because there's more things to integrate. So we have to come up with something that's much more flexible. SME knowledge resides in people's heads. This is the biggest thing. Fortune magazine just put out an article this month asking why people are claiming that big data projects are not working, even though they're investing millions and millions of dollars in them. The answer was they're not actually solving the real problems. People are using MapReduce, they're using Hadoop, they're building NoSQL databases, they're building data lakes. To what end? What's the problem they're trying to solve? Okay, that's not often very well understood. Okay? I've spent most of my career spanning the gap between the people sitting in the C-level boardroom and the people sitting in the laboratory, because to my knowledge, that's one of the biggest silos that are there. That's one of the biggest gaps in any organization to overcome. Where's the company trying to go? What are you trying to do? Where's the next innovation? Where's the next big driver? And what are people who are down in the weeds actually building, right? Are they just building things that make some job easier for themselves, but it's not really part of a global process or path? Understanding this information is key. You have to know what's in people's heads. The reason why ontologies have also failed is because we've done a poor job oftentimes of building the models that allow people to really take concepts out of their heads and put it into the software, into the data. Instead, we just build data models that look just like all the rest of the data models we have, except they're in a graphical structure. So big deal. But we all know from working with each other that concepts, specifically as they're captured in language, can be really, really important. I could point to anything in this room, this, and I could ask someone to please raise their hand and tell me what it is. And I bet that even though some people here are not native English speakers, we come from different areas, there's both men and women here, we have different cognitive constructs, different backgrounds, different belief sets, and so on, we could come to some type of organized thought about what these objects are, what they mean, how they're used, how they're not used, and so on. Right? This is communication. This is how we work conceptually as people. This is what we need to put inside of our systems. But it's very, very hard because machines are inherently stupid. They don't grow up with a background. They don't have a childhood. They don't have belief structures that come from something else. And they don't really perceive things in the world the way that we do. But what we're talking about here is really reference. You have to have common reference. When I point to this thing, what's it called? Is it called a podium? Is it called a lectern? What's it called? It doesn't matter, right? We can give it different labels. We can have different uses for it. It can be the doorstop if I need to hold the door open, right? It can be cover if I need to duck behind it. It can be lots of things, right? It depends on the context. It depends on my use value. So if we can get this knowledge out of people's heads, which is not impossible to do, it just involves talking to them. We can put this information into good models, and we can use those models then to connect how different people in our organization are speaking about our data, are talking about our experiments, are talking about their jobs, the business values, the drivers, and so on. Last, the data schemas are not therefore explicitly often understood, okay? And therefore, you get a lack of common vision between business units and scientists. So because we don't get the information out of people's heads adequately, we also don't really understand how it ties to the data. We don't understand the structures that people are using. We don't take the time to say, what do you mean? So here's a picture I like to show from a former customer of mine. This is actually what happened inside of their R&D shop. They had to start an initial step. If they needed to find something out about a product that was made, they could only do a protocol search on a lot number, period. If you didn't know the lot number, then you couldn't start the search. You couldn't get any information for regulatory. You couldn't get any information to go to production. They didn't know which projects led to which product, because on average there were 7 to 8 projects spread over 8 to 10 years that made a product. And so this person had to find a lot submission, and then had to go to this poor, sorry fellow in the middle, whose job it was to collect all the information for some regulatory body. So this person had to go query LIMS systems, had to go to a separate person for instrumentation to go query a whole different set of databases, had to go to the marketing people to find out what's all the other packaging information and things that were done around this product. They had to go to get the lot and manufacturing info, so there was an R&D tech down there that, of course, had multiple databases that this person was in charge of. They had to go then look for start and completion in the production data itself. And then once they pulled all these things together, they gave it over to their external regulatory affiliate who checked it, handed it back. It went over for verification to go to the FDA or some other regulatory body. And guess what? It was 99% of the time wrong. It was missing data. It was incorrect. Calibration settings weren't there, what have you. So guess what? It started the initial step. Go back, now find more lot numbers, and go through this process again. This process took, on average, 5 to 6 weeks to produce one report. We built a semantic system in a cloud for this customer that removed this barrier. It basically took that person in the middle and it put a system in there, put a machine in there. This went to 12 to 40 seconds, and anyone could do it from their laptop inside the company. So it's not only about cost savings. What we saw here was we saw a drive in innovation. This customer went from all of these manual steps and all of this manual data correlation to the ability to pull it together quickly and easily and produce reports that were 100% accurate and knew all the information it needed to know because it was all integrated on the back end, right? It took probably about 1.5 years to do this, but the outcome was R&D suddenly was connected to regulatory. R&D had better connection to manufacturing. R&D had better connection internally, and so on and so on and so on. This was a fairly monumental step and was one of the largest semantic cloud integration projects that I personally know of. And the value of this is that it really changed the organization. It just changed the way that these people thought about their data, which leads me to the next point. Why does data matter? Data matters, and I'm going to make probably a inflammatory remark here, because I know how much your products are all worth. But actually, data is your most valuable corporate asset now. Companies that have figured this out a few years ago were Amazon, Google, these guys, Apple, right? They figured out Facebook, correct? They figured out that having data, right, whether it's data on people, data on consumers, data on your products, whatever, is more valuable than the things you're making, right? Because that's what's showing you the trend for the next things. That's what's showing you how things come together. Furthermore, your enterprise systems are increasingly becoming hybrid. This means you have legacy systems, you have everything back from old Fortran systems, COBOL, you've got databases, relational databases. Hopefully none of you still have Turing machines and punch cards, but you've got these old relational databases. You've got this new technology coming in, so people have probably said, hey, let's go to RDF and semantics and OWL. You've got Excel. You've got structured, semi-structured, unstructured documents, text, what have you. Now you've got things in social media, which is one of the largest growing areas in data these days, right? What are your customers saying about your products? What are people liking and disliking? What's going on with your competitors? What's happening out on the Internet of Things? Okay? Legacy data sources need to be combined with this new tech, right? This is just the way of the world. So this is the way that Gartner sees it. This is the way McKinsey sees it. This is the way that many people in the modern world are moving towards. Therefore, if these systems are becoming more hybrid, the integration of this data is becoming naturally more complex. The size of the data sources are growing. I'm sure you've all heard the statistics. 90 to 92% of all of our data now is developed in the last 2 to 3 years, right? And that's increasing. There's different user groups now within organizations. Different people now want to use data sources to make decisions. Answers need to reflect increasingly complex patterns. Okay, this is no more about just basic storage and query. Finding and utilizing the key data within an organization is of increasing importance. That's why the data is the most valuable corporate asset that you have. The fundamentals, therefore, of the management of this data have changed. Basic storage and retrieval has given way to things like analytics and responsiveness. People want near real-time decision-making. People want answers pushed to them. They want automated queries. Right? They don't just want to say, okay, here's the pile of data I have, and here's a bunch of clunky dashboard tools, and now you can spend half of your day, driving around trying to find some answer in there, right? With some probability of success, right? People want this stuff automated, and they want it deliverable. Analytics and data science for the 21st century is taking off because the rate of this digital information is also growing exponentially. So the type of information and the rate at which it's flying at you is increasing. Cloud computing is now critical for scaling enterprises. You have to have some horsepower behind these things. Again, this is why the semantic push has failed in the past. I built some very cool systems when I was younger, and I would always get to some point in the organization where I got in front of some big decision maker, and they'd say, okay, but does it scale? And I'd have to go, not really. It solves this neat little problem, though. Isn't this cool? Look, we have a graph, and I can write this query, and it's better than SQL, and it didn't matter, right? The bottom line was it wasn't ready to go enterprise-wide. It wasn't ready for prime time. Cloud has fixed this. We now have lots of horsepower. We can run things in multi-node clusters. We can have information through secure HTTPS web services, microservices, whatever you'd like to build that go right to your laptop, your tablet, your phone, whatever you would like, okay? New data types are also being created, and these things hold significant value. A lot of the really important data in your company isn't in your raw data. It's in understanding the patterns of how people are using your raw data. It's in understanding how that data comes together, and it's in understanding what it means. That when we start pointing to things in the world, we understand the referent that we're pointing to, and therefore we know the raw data behind it. If I point to the chair, right, and I ask a physicist what I'm pointing at, he's going to tell me things about particles and waves and, you know, color doesn't mean color like it does in the regular world and so on. Okay, that's just an explanation. That's perhaps raw data. My eyes interpret things, it flips an image upside down in my brain, it does all these different things that I'm cognitively unaware of. But when I point at the chair, I mean the chair. And the key here is that your raw data has to mean something now, right? These new types of data that are being created are really data around patterns. The patterns are what are important. This is where we're going to get personalized medicine. This is where we're going to get all this interesting stuff that people are talking about in the popular press. Therefore, data is becoming more personalized and more context-based. People want their own data. They want their own answers, and they want things to make sense in some type of a context, right? So in order to do this, we have to understand that the effect of data is therefore changing our business landscapes. Everyone is undergoing this process of change. As I said, 90% of the world's data was produced in the last 2 years. So I always ask people, how well can you mine and leverage this data? What's it worth to your company to be able to do so, right? These are important questions to ask. An interesting statistic I found was that $900 billion a year is the cost of lowered employee productivity and reduced innovation from information overload. In other words, big data is choking companies at the cost of almost $1 trillion. It's not because we don't have data, it's because with all of that data, how do you know how to use it? How do you avoid that cost, right? So if we look at McKinsey, and this is a bit of an old quote, you'll notice it's from 2011, okay, it's 5 years old now, but I like it because it's prophetic. Because when they said this, a lot of people went, eh. But increasing the volume and detail of enterprise information, multimedia, social media, and the Internet of Things will fuel exponential growth in data for the foreseeable future. Correct. That's happened. And the use of big data will become a key basis of competition and growth for individual firms. Again, correct. I think that's happening. So the key here is that we're seeing the rise of analytics, a new kind of analytics. We're seeing the rise of a new kind of data that we're talking about. And the ability to harness and pull these things together requires a different approach, a different kind of philosophical approach. So, enter semantic technologies. And by the way, I include semantic technologies as part of data science. Okay? And I'll explain why in a moment. Semantics has its origins in philosophy. It's generally understood as the abstract study of meaning. Okay? So Edmund Husserl in 1900-1901 wrote this great 2-volume book called The Logical Investigations, and it was the first real treatise on formal ontology. Okay? You also have a host of other philosophers, Kant to Heidegger, who talk about things like being, and they talk about how we understand things. It really has to do with meaning. What do we mean by our data? What are the concepts that are in there? What are the things you're using that data for? What does the data represent? It's distinguished from syntax. This is an important distinction. Syntax are the markings or the language someone uses as a rule-based grammar, right? So the letters we use in the English alphabet versus the different characters you use in Arabic or in Russian or something like this, that's syntactic, right? XML versus RDF is syntactic. It's just a syntax. It really doesn't matter. What you care about is the meaning behind what you're representing. So, if I ask, what do we mean by Washington? Well, we have a president, we have a city with some nice monuments, we have a state that, by the way, is on the complete opposite side of the country from the city with the nice monuments. There's a bridge I can take in New York. There's a football team that has an inflammatory logo that people talk about a lot. There are people like Washington who played for the Jets. And then there's a baseball team who does not have an inflammatory logo that many people talk about, right? So all these things mean Washington. So what do you mean? How do we use the word Washington? I mean, how do we ever do this? Well, it's because of context. If we're talking about presidents, then we know we're not talking about bridges and monuments and things. However, presidents have something to do with Washington, D.C., right? So Lincoln was a president, and Lincoln has a monument, so you can talk about Lincoln as the president or the monument, right? But it's about the context. It's about pointing at the thing and saying, what do you mean? And when we talk, we use lots and lots of cues for these things. The key for this in semantics is you have to build these cues into the models that go into your systems. This is why it's not about just top-down, bottom-up approach. Okay? That to me is very old thinking. It's both. Application-based formal ontologies. I published a paper on application-based formal ontologies back in 1999 and said, look, you have to work from the top down and the bottom up at the same time. That's what engineering is. So if we look at the evolution of these items, right, we see that code used to be more important than data. Then you hit the relational data model era. Data became as important as code. And now, thanks to the semantic web era, the data is more important than the code. It doesn't matter what it's written down in anymore. I can take my RDF, I can turn it into XML, I can shoot the file over to someone else, they can open it up and then reconvert it back into RDF if they want. Doesn't matter. What matters is, did the class structure stay in place? Are the relationships still labeled the same? Is the hierarchy the same? The other thing I'll say about taxonomies, and this has to do with some of the work we're doing at Allotrope, there are two ways to build taxonomies. This also has to do with the top-down, bottom-up business. If I take a very, very rigid notion of a taxonomy as a class structure, right, with subsumption relations, in other words, where I have ISA, Eric Little is a human being is or Homo sapien, which is a mammal, which is a carbon-based life form. Okay, that's showing me clear ISA connections, subclass, superclass relationships, structured, ordered, right? This is a top-down approach. This is how I know we can use the same kinds of words. But we also use things like SCOS definitions, right, where we use broader and narrower terms, right? We can say, well, this term is just a broader term, or there's a whole bunch of synonyms that I can use for these terms for the same concept. It's a different way of approaching taxonomy construction. Both have to be adapted. So it's not just about subclass, superclass, and it's not just about word relationships. Both have to be used. So in a subclass, superclass, you have acyclical tree graphs, real hierarchies. The other way looks like WordNet. You have graphs, right? You just have words generally in a network related to other words. In Allotrope, therefore, we're doing both. So we have certain structures that we put in for things on equipment, material, process, and result. We do our work in metaphysics to make sure that we have the structure of the universe kind of correct, right? To say that a mass spectrometer is a spectrometer, which we're calling a device, but there are other devices which are not such things. And we know that, for example, a process is an inherently temporal thing, whereas a piece of equipment is not. It's a spatial thing. So I describe the parts of spatial things differently than I describe the parts of temporal things, because temporal things are never standing still. They're always going through some process. They're in a state of constant becoming and fading away, right? And for any of you who know about ontology research and you go look at the work in BFO, the Basic Formal Ontology, out of the University of Buffalo, where I worked with Barry Smith, this was the idea behind this, snap and span. So we are incorporating this into Allotrope, and then we use these basic structures, and you can see how basic this is, to then do this kind of SCOS, broader, narrow types of terminologies. So where do we go? We go from code and lists, basic data, to terms. Things like soil, plant, drug, compound, whatever. Then you build a controlled vocabulary. So let's agree upon some terms. Are we going to call this thing podium or lectern? Which one? We could take a vote and we'll say the preferred label will be podium, but if you look up lectern, it's going to point to the same thing, right? That's all we're saying. Control vocabularies give us taxonomies. Now we can put things in a hierarchical sense because things do in the universe exist where they should be. We can then build thesauri. We can then build RDF graphs. We can move to OWL ontologies and eventually get to things like reasoning, rule-based logics, and new patterns. So I'm not going to spend a bunch of time on the levels of semantic expressivity because I'm just about out of time. But basically, you have weak and strong, and you can use your knowledge representation to separate the schema level from the data level. This is what's really important here. We're keeping the concept separate from the data. We all know these benefits. You get interoperability, better searching and browsing, reuse. You can show architectural intent because I can put all kinds of notes in there. I get automated reasoning if I want, and I get a nice developmental life cycle. And then when I move to analytics, what I'm able to do, if we look at this example from the chessboard, you know this old fable of the emperor who brought in the peasant and asked him to perform a job for him, and he said he would if he puts 1 grain of rice on the chessboard, and for every square on the chessboard, just double the grains of rice. So the emperor thought, well, what a great deal. Sure, a few grains of rice, right? Well, until you get to the end of the chessboard, and you realize that what the guy is basically promising is 461 billion metric tons of rice, which is roughly 1,000 tons more than was produced in 2010 globally. So what this means is that on the second half of the chessboard, as you keep doubling, right, you wind up with very big numbers. This is where data is going. This is where analytics is going. The key here is that we used to worry about processing speed. We shouldn't. Processing speed grew 1,000x between 88 and 2003. Algorithm design grew 43,000 times in that same time period. So it's a 43-to-1 increase in the complexity of the algorithms versus the complexity of what we're doing. 4 V's of big data. I'm not going to spend a bunch of time in this except to say where we're sitting with allotrope and with the semantic part is in the variety space. Volume velocity, people know. Veracity has to do with clustering, mathematics, and uncertainty. Probability sits there. The key here is to bring those two things together, the variety and the veracity. So why do the semantics matter? Because big data approaches require proper metadata. All your algorithms run on classifiers. What do the classifiers refer to? They're going to refer to different things based on who built the classifier. If you have a nice reference data model, your classifiers now align. Relationships matter, therefore understanding perspective and context is critical, so you have to understand more about the data than what's in the data, and you have to have better models and schemas. Therefore, my last thought, where I think smart labs in the future go is this list. We have integrated data with common reference data structures in the form of vocabularies in these taxonomies. We have shareable data, so you have easier interaction across teams and business units. You can now link the scientists to the business folks. You get scalability because of big data applications. You get conceptual representations, so now you have context and perspective. We can talk about things in a variety of ways. And this all leads to ultimately advanced analytics, which is a way to really blow up the world and talk about things in new ways and apply logic with mathematics at the same time. It's something my team and I are working on right now. So with that, I'll be here both days if anyone wants to stop by and chat more about these concepts. And thank you very much. Enjoy the conference.